So welcome back, and in the last class we have seen about simple exponential sequence, say a sequence there we had for continuous sequence we had e raised to 80 where the function depended upon the value of a. Okay, that is when the value of a is 0, then that is a constant. That is there is no decaying or rising. But if a value of a is greater than uh, greater than 1, then that is a rising signal, an exponentially rising signal. And if that is less than less than 1, that is a decaying signal. Okay, so now today we see about a complex exponential signal. So now we have a signal of the form x of t is equal to a into e raised to st, and instead of a we have a complex variable s. This is a Laplacian operator or Laplacian variable, and s is having real part and imaginary part, and that sigma is s is equal to sigma plus j omega. Okay, now if we substitute instead of s this value, that is it becomes e raised to sigma plus j omega whole multiplied by t, and I am opening a into e raised to sigma t e raised to j omega t. Okay, and we know that e raised to theta t is nothing but cos theta plus j sine theta. So instead of theta we have j omega here, and sorry, instead of theta we have omega t here. So substituting that value we get a, this is the common thing, that is a into e raised to sigma t, the whole thing multiplied by cos omega t plus j omega t. So this function, this whole thing will give sinusoidal oscillations. Okay, now the whole thing will depend on the value of sigma. Okay, that is, suppose if s is equal to 0, for s is equal to 0, then what happens? If s is equal to 0, then anything raised to 0 is 1. The magnitude is constant at a, irrespective of the time, irrespective of the variable or frequency. Everything is constant at a. It's a DC signal. Okay, now if sigma is negative, then what happens? If sigma is negative, then this value is negative. Okay, so this omega is 0, so oscillations are 0, only sigma is negative. So just like the previous thing, it's a exponential decaying signal. Okay, now if sigma is positive, here also omega is 0 but sigma is positive, so what happens? It becomes an exponentially rising signal. Okay, and one thing you have to note that this curves meet the y-axis at the point, uh, this point where we have that is at this point uh, t is equal to 0. At t is equal to 0, what happens? At t is equal to 0, the whole thing is anything raised to 0 is 1. It will be having a magnitude a. So the crossing point, the magnitude of the waveform will be a. Here also at the crossing point, the magnitude of a will be, magnitude of the signal will be a. Now we have the other case, that is, suppose if sigma is 0 and j omega is having some value, then that means it is having oscillations. They are having sinusoidal oscillations. So what happens? That is, it's a simply undamped oscillations. There is no damping factor, okay, or undamping factor. Okay, simple oscillations. It will continue like sustained oscillations. Now suppose we have sigma and j omega, they are both having values, but sigma is having a value less than 0. Then sinusoidal oscillations are there, but the oscillations are decaying as time progresses. Okay, and at one time the oscillations die out and becomes 0. And the opposite happens when sigma is greater than 0. That is, j omega as well as sigma is having values, but sigma is having greater than 0 value. So what happens? It starts off with a simple amplitude, but amplitude rises, exponentially rises as time progresses. Okay, now we'll similarly move to the next one, that is the uh, discrete one. Here also the same thing. A raised to n is the simple exponential thing, but a raised to n is multiplied by e raised to j omega naught n plus phi, where omega naught is the angular frequency and n is the points and phi is uh, the phase difference. Okay, here also the same thing, just like the other thing, that is, if a is greater than 1, if a is greater than 1, suppose we have 2 here, what happens? So this e raised to j omega will bring sinusoidal variations, but or the whole thing, whether it is undamped or damped, everything depends on the value of a. So if a is greater than 1, suppose if I take 2, so 2 raised to 1 is 2, 2 raised to 2 is 4, 2 raised to 3 is 6, it goes like that. So what happens, the whole thing, if it is multiplied by such a thing, it exponentially grows, the amplitude exponentially grows. But rather, if you have a value less than 1, what happens? So if a value is less than 1, then what happens? That is, suppose if I take 0.5, so 0.5 raised to 1 is 0.5, 0.5 raised to 2 is 0.25. So what happens? The amplitude decays exponentially as n progresses. Okay, so that is the thing about discrete time signals. Another function which you have to keep in mind is the rect function, or it is called pi function, or it's sometimes called gate function. Okay, so the symbolic representation is this one, that is rect of t by tau. Okay, so this signal is simple when we see the figure, that is having a magnitude 1 between minus tau by 2 and tau by 2. So it's an even that function, that is mirror images here. Okay, that is this portion mirror images here. Okay, now this is a way of representation, that is it is having 1 between, so irrespective of the value of t, that is if t is that it's having a value 1 for t less than or equal to tau by 2, that is t less than or equal to tau by 2, it is having the value 1. Okay, if the value t is negative, then for minus t greater than or equal to minus t less than or equal to tau by 2, so this is the value. So irrespective of the value of polarity of t, it is all 1 between tau by minus tau by 2 and tau by 2. That's a simple rectangle function or rect function. This is not necessary to be learned, but signum function is very important. It's another simple function, that is it is having a value 1 for t greater than 0. For t greater than 0, it is having all ones, but for t less than 0, it is having minus 1. So this 1 goes till plus infinity, and this minus 1 goes to till minus infinity. Now what there is no mention about what is happening at t is equal to 0. This is t greater than 0, this is t less than 0. So what happens at t equal to 0? So at t is equal to 0, the value is having 1 and minus 1. So 1 and minus 1 gets cancelled each other. The value is 0, effectively 0 at t is equal to 0. Okay, now can I write signum function as minus 1 plus 2 u of t? So what is 2 u of t? That is 2 u of t is that u of t is multiplied by 2. That means my magnitude will be 2 here. That is magnitude will be continuing with 2 till plus infinity. Okay, from that if I subtract minus 1, so what happens? I'm having there is no signal like this. But what is 2 of u of t? U of t is all ones from 0. The greater the t greater than or equal to 0, it is all 1, continuously 1. If I multiply that with 2, then the magnitude becomes 2. If I subtract this, the whole signal with minus 1, what happens? If I subtract minus 1 from this signal, what happens? The magnitude 2 will become 1 for t greater than or equal to 0, and 2 u of t does not have any value for t less than 0. So what happens? Obviously when you subtract minus 1, so what happens? 0 minus 1 is all minus 1. So you can write it as signum of t is minus 1 plus 2 u of t. Another function is sing function. This is also a very important function. That is sing function of t is t sine t by t for minus t less than t less than infinity. So between minus infinity and infinity, this function is there, and it oscillates with a period 2 pi, and it is another important thing is that it is having natural zeros at all multiples of pi, that is at pi, 2 pi, 3 pi, 4 pi, likewise minus pi, minus 2 pi, like that. Okay, so it's an even function. What's an even function? That is when you look at this, when you keep this y-axis as a reference, same thing happens. The mirror reflection of this thing happens here. That is the function, that is a peculiarity of an even function. Okay, so I am just leaving this portion, and you have to evaluate these integrals as homework. Okay, that is, I'll just show 2 examples. See, what is this function? That is, leave this portion alone. We have integration from minus infinity to infinity delta of t minus 5 dt here. delta of t minus 5. So the whole integration will have a value only at t is equal to 5. That is that's an importance of analog impulse. Okay, this whole integration will have value only at one point, that 2 at t is equal to 5. So what is happening? What is the value at t is equal to 5? The value at t is equal to 5 is 1. So the whole integration suffices to 1, and that too at t is equal to 5. So 1 multiplied by e raised to minus a into, instead of t I can substitute 5. So the value is e raised to minus 25a. Right. Likewise, you can have this, you can see this integration also, that is at this point the whole integration suffices to one point, that is at t is equal to 6 and the value is 1. So if I substitute 1 multiplied by instead of t I can substitute 6, so 36 is the value. Likewise, you can solve the whole thing as homework. Okay, now the next thing we have to see is that was for the analog impulses. Now what is the importance of digital impulse? Digital impulse also is very simple. Instead of integration we have summation. So this summation suffices to 1, and that is at only one point, that is n is equal to 3. This whole summation, even though n is from minus infinity to infinity, we are performing summation from minus infinity to infinity. Since we have a digital impulse, this impulse is having only one value of magnitude 1 at n is equal to 3. Okay, so the whole summation reduces to e raised to 3 into 3, that is e raised to 9. Okay, that is the answer. And here what happens, the whole summation has only one value, that is at n is equal to 2. What is the value of this one at n is equal to 2? 1. So what is the whole summation? The whole summation is cos 3 into 2, that is cos 3 cos 6. Okay, likewise we can solve these ones. What is the last one? The whole summation suffices to a value 1 at n is equal to minus 1. So what is the value? 4 raised to minus 1 is the value of this entire summation. Okay, now we will move on to some basic operations. That is, we have some basic operations. We'll see the first two very quickly. If time permits, we'll see the third one also. And that is time shifting. That is, if I have a continuous signal x of t, so this is my x of t. If I delay that, if I shift that signal by t seconds or time, this is called time delay. We can delay the signal or advance the signal. That is called time delay. Okay, time delay or time advance. Okay, so if I perform y of t is equal to x of t minus capital T. Okay, then what happens in the above equation? If t is positive, the shift is to the right, and then the shifting delays the signal, and if t is negative, the shifting is to the left, and then shifting advances the signal. So we'll just see the waveforms here. That is, see, so x of t is here. This is my x of t of magnitude a between 0 and 6. Suppose if I am performing x of t minus t, then what happens? I am delaying in time the signal. So the signal starts at the argument is equal to 0, that is t is equal to t minus t is equal to 0, that is t is equal to t. So the signal starts at this point. So instead of starting at 0, now the signal starts at t. Okay, now earlier the signal truncated at 6, now the signal truncates at or ends at t plus 6. Okay, now if we have x of t plus capital T, now what happens? The signal starts at the point when the argument is equal to 0, that is at t plus capital T is equal to 0, that is at t is equal to minus capital T. Now see, the starting point is at minus t and the ending point is at initially it was at 6, now it is advanced by t seconds, that is minus t plus 6. Okay, so if t is negative, then that is delaying. Sorry, if t is positive, that is delaying, and if t is negative, then that is advancement. Okay, now similarly that is applicable for digital signals also. That is, I can delay the samples by digital sequence by case samples or advance by k samples. We will see immediately in the next class. Thank you.